the inner product. Suppose A and B are two vectors in R2. Then we define the inner product of A and B as A1 times B1 plus A2 times B2. We denote this inner product by a big dot times B. Sometimes this inner product is also called the dot product. Of course, we can do this in any dimension. If we have a vector A which is A1, dot 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 AN, and B is B1 dot 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 BN, then their inner product is A1 times B1 plus A2 times B2 plus AN times BN. This inner product is sometimes also denoted in the way that you see now, using these pointed brackets. Here are some properties of this inner product. The length of a vector is equal to the square root of the inner product. If we have two vectors, then we can let them start at the same point and we can find an angle between the two directions. So let's say this angle is called alpha. Then cosine of this angle, cosine of alpha, is equal to the dot product of A and B divided by the length of A times the length of B. In other words, the dot product between A and B, or the inner product between A and B, is equal to the length of A times the length of B times the cosine of the angle alpha. Here are some more properties of this inner product. X inner product X itself is of course the length of the vector X, so is at least 0. On the other hand, if X inner product X equals 0, then its length has to be 0, so the vector X is 0. Of course, X inner product Y is Y inner product X. That's just like multiplication of the reals. And finally, if we multiply X with a scalar lambda, and then take the inner product with Y, we get the same result as first computing the inner product X and Y, and then multiply it with lambda. Of course, this easily follows from the property we saw before, that the inner product of X and Y equals the length of X times the length of Y times the cosine of the angle alpha between the two vectors. If I multiply X with a lambda, then only the length of X will change and not all the other parts. Two vectors A and B are said to be orthogonal if their inner product is 0. We denote that by A perp B. You see the symbol for this. This of course agrees with the formula that the cosine between the two vectors, of the angle between the two vectors, is equal to A inner product B divided by the length of A times the length of B. So if the numerator is 0, then this cosine is 0, and we find that the directions of A and B are perpendicular to each other. Indeed, if we have the vectors 1, 0 and 0, 1, then they are perpendicular. Their inner product indeed is equal to 0. But also the vectors 1, 2 and minus 2, 1 are perpendicular to each other. That's easily checked. The inner product is minus 2 plus 2 is indeed 0. But that makes it easy to find all vectors perpendicular to a given one. Which vectors are now perpendicular to 1, 2? Well, these are all the vectors x, y, such that the inner product with 1, 2 is equal to 0. So we have all vectors x, y, such that x plus 2y is 0. find a vector perpendicular to a given vector, we can just switch the two coordinates and change the sign of one of them. So if we start with 1, 2, we just switch them around. It's 2, 1, and put a -1 for the last vector, and find 2 minus 1 to be perpendicular to 1, 2. -2, 1 is also perpendicular to 1, 2. Indeed, the inner products are 0. And also all multiples of -2, 1 or 2 minus 1 are of course perpendicular now to 1, 2. The vectors which are perpendicular to a non-zero vector AB, they form a line given by the equation ax plus by is 0. Any line parallel to this line is given by an equation of the form ax plus by is a constant c. The vector AB is always perpendicular to these lines. It's called a normal vector of these lines. For example, if we consider the line through the points 1, 1 and 3, 4, then a direction vector of this line is, of course, 2, 3. The vector 3 minus 2 is then perpendicular to 2, 3 and is therefore a normal vector to the line L. And then we can find an equation for this line as 3 times x minus 2 times y. That's the inner product of 3 minus 2 with a vector xy is equal to the inner product of 3 minus 2 is one of the points of the line, say 1, 1 or 3, 4. If we take 1, 1, we get 3 times 1 minus 2 times 1 is 1. The vectors on the line have constant inner product with the given normal vector. If we have two lines L and M in the plane that are perpendicular, then the equations of these lines are, say, y is ax plus b, and M has the equation y is cx plus d. We can easily find no normal vectors. Namely, a normal vector for L is a minus 1, and a normal vector for M is c minus 1. As the lines are perpendicular to each other, these normal vectors are also perpendicular to each other. But that means that AC plus 1 is equal to 0. So A times C is minus 1. And we have that the two slopes, A and C of these vectors, have product minus 1. So any two perpendicular lines, L and M, have the property that the product of their slopes is equal to minus 1.